Okay, so last lecture we talked about Gibbs free energy. And we know that if the sign of delta G is negative, the reaction is spontaneous. That means the reaction will happen at a energetically favored condition. So if your delta G is positive, that means you need to add additional energy to drive the reaction. So free energy is basically talking about the available energy for a reaction to happen. Okay, so when we talk about this term, the enthalpy, this is generally comes from breaking the bond and forming a bond and the surplus of the energy. That gives you delta H. Okay, and in the last lecture, we have derivation trying to account for the change in pressure. Okay, so for the Gibbs free energy term, usually there's another term that deal with the change in work that's done by the expansion of gas. Okay, and but generally when we are talking about this equation, we assume it's constant pressure because we're doing these very small steps. So we do not account for the change in the work done by the expansion of gas. Okay, so that term goes away. But that term is generally accounted by enthalpy change. And then we talk about delta S. Delta S is the term for entropy. That means randomness and disorder. When you are producing a lot of gas from your chemical reaction, you are increasing the entropy, right? So you will get a positive number. But if you are freezing the water molecule, turning it from liquid to solid, you are decreasing entropy. If you are dissolving sodium chloride, when it dissociates into ions, you are increasing entropy. But for water, since your salt has to be solvated, so locally around these ions, your mobility of water decreases. So you are decreasing the entropy when we look at the ions. That all make sense? Even for a endothermic reaction where you have to absorb heat, if your delta S is big enough, or this term dominates the reaction, delta G will still be negative. Okay, so you have to understand the sign. And then in the previous chapter, we talk about Q and K. Q is to describe the state of a system at a certain time point. And K is referred to chemical equilibrium. So we know when you are at the equilibrium, your delta G is 0. There's no forward and backward reaction. Then we can actually calculate how far away we are from equilibrium by using the delta G calculation. So generally, there's an equation where, so this is very similar to calculating the probability of these microstates. So you may remember that delta S, you can use equation that is a function of natural log, right? So for delta G, similarly, you can get delta G is equal to RT. And if the Q equal to K, this term will become 1. So that satisfies your assumption that at chemical equilibrium, at infinite time, when there's no more reaction that could happen or drive, and no more energy available to drive such a reaction, you will get a delta G of 0, right? So in a real scenario, when you mix reaction together, at the beginning, your Q would not equal to K yet. From this equation, we can solve for how the delta G is dependent on equilibrium constant. Okay, this K is equilibrium constant. So just a simple mathematic operation, right? So if we, under standard state, we can say Q is equal to 1, right? You have equal amount of your product and a reactant. So this term go away because it's 0. And then you can, in the end, you get delta G equal to negative RT and times natural log of your equilibrium constant. From this equation, what we can do is when the delta G is given, for example, in the sample problem 20.9, so you can calculate delta G from the equilibrium constant, and you can calculate equilibrium constant from delta G. So what does that mean mathematically? We know K is product over reactant. Usually for a energetically favorable reaction, you will end up with a lot of products with very little reactant, right? For a very energetically unfavorable, or usually we will call it unreactive system, you will have a lot of starting material that you put in and very little product, little to none. So in that case, the natural log take care of it. So that's what it means to have this equation. So it's really depending on how big of this term is, and that will dictate your delta G. So, and we know when the delta G is negative, it's energetically favored. So you can look at table 20.3. So it basically just tabulates out all the values, like what I just said here. When you have an extremely large number, you have an extremely negative delta G. The way you look at it is either giving out a lot of heat or increase the entropy by a lot or at an extreme temperature. Okay? In the last lecture, we talked about how to think about these terms relative to temperature. It really depending on the order of magnitude of your delta S and delta H. And be very careful in the textbook or your exam, the delta S will be given in joule, where enthalpy will be given in kilojoule. Okay, so you have to watch out for the unit difference. With this equation, or with this natural log Q, we can find at any instance of your chemical reaction, we can find out how much free energy is available. So what we can do is we can use this equation where delta G is equal to delta G prime, that is the standard state, plus RT natural log Q. Remember, this Q is reaction quotient, and then that's what you get from the product over reactant. If you have a stoichiometric factor in front of your chemical formula, such as a more complex reaction, such as, for instance, if you convert N2O5, if you have a decomposition of N2O5, you will have these factors in front of your decomposed products. So you will have to account for these factors as the exponent to your concentration. So by using this equation, you can figure out how far away you are from the equilibrium. Okay, so this is some mathematical calculation that you will need to learn. Okay, how is this thing useful? In the electrochemistry, we basically talk about 3 sections of electrochemistry because we did not discuss free energy yet. Now with this equation, we can actually do more calculation on our electrochemistry section. If we think about any given electrochemical system, why does electrochemistry happen? When we mix zinc powder or with copper ion solution, oxidation reduction reaction happens instantaneously. By happening instantaneously, we know that delta G is negative. How does delta G relate to the potential of your redox system? So that goes back to chapter 21 in the section 21.4. It's known that delta G is proportional to the potential of your cell. Okay, so when we're talking about potential, the energy always goes from higher state to lower state. So when for a redox reaction to happen, it goes from a high chemical potential to low potential. So we know this is proportional, right? So from the experience, we know when we're charging the battery or discharging a battery, it heats up. The battery heats up. It's a very common scenario, right? So why does it heat up? Because based on the way things work, it's really hard to get maximum efficiency. There are going to be some small amount of energy is wasted because of heat, okay? And if you think about the redox processes, you have something being reduced, right? And something being oxidized, okay? You're forming ions, right? And their solvation power of your electrolyte is different depending on the type of ion that you have. Okay, zinc ion versus copper ion, they're all different. Your delta S is different. You have this enthalpy term. Okay, so if you think about what's happening in a battery and think about delta G, I hope you can see some connection there. So we know electron has charge. So we already know how to balance an equation. So we can account for that. There's something called Faraday constant. Okay, so that is basically giving you a quantification of the amount of charge that you would have per mole of electrons. You can think of it as a correction vectors for the calculation that you're about to do. Okay, so like I said, the work done by a redox cell or basically a battery is basically proportional to the potential that you have and the charge involved. Because what is electricity? It's basically electron moving from one end to the other end, from higher potential to lower potential, from anode to cathode. Then basically, how would you relate these two together? It basically comes down to delta G equal to negative number of electrons involved in the system, Faraday constant, and your standard potential of your cell. So that will give you, using this relationship, and combining with this equation, delta G equal to negative RT natural log of K, you can naturally obtain how much energy is left from a battery. Why does battery die? Because its own chemical equilibrium. So if you're far from the equilibrium, for the reaction to happen, we basically take advantage of electron transfer and utilize that chemical energy in the form of electricity. Okay, so if you balance the equation, if you're combining this equation with this one, what you can end up getting is, okay, now you can do some calculation based on such equation, okay? Because we know this is constant, we know usually you operate at a standard temperature, which is room temperature, right? So you can simply get the value of this, so this is a constant too. So that's what you end up getting. So then you can calculate, based on this equation, you can do a lot of calculation that will tell you the free energy that's available from a battery or from any redox reaction. Okay, so similarly, given this equation, we can calculate how far off you're from the standard state, which is at equilibrium. So we can do some substitution, then we can easily end up getting any state of your potential of your battery, and how far away are you from the equilibrium? And it's a very similar form, minus, this is a number of electrons that involve in each redox cycle. Then you have log Q, so at any given state. Because why this is Q? Because it hasn't reached the equilibrium, right? So when the Q equal to K, you don't have any energy left. That makes sense? So if this is K, I mean, this is go back to, you have no more extra energy left. So you can see the similarity between these two equations. When people first develop battery, we wonder about its thermodynamic parameters. Okay, so these equations will explain the maximum amount of work a battery can do. By doing these calculations, it's pretty straightforward. So like I said, when the Q is equal to K, this will become 0, and that's when you know it's at chemical equilibrium. So I mean, for this weekend, I would like you guys to read 21.7. If you haven't read chapter 20 yet, I'll encourage you to do so and work on these problems so you understand what's going on and what to do with these equations. Any questions?